Hello everyone, in this video we will cover the section 2.5. In this section we will see autonomous equations and population dynamics. Autonomous equations are an important class of first order equations. In these equations the independent variable doesn't appear explicitly. Such equations are called autonomous differential equations, and they are a subclass of first order differential equations, and they have the form dy over dt is equal to f of y. Namely, the right side of the differential equation is just a function of the variable y. Namely, we don't have any term related to independent variable. In this section we will discuss this equation in the context of the growth and or decline of the population of a given species, an important issue in fields ranging from medicine to ecology to global economics. First of all, let's remember some general formulas for some differential equations. First order differential equations have the form y prime is equal to f of ty. This is the most general form. And if you remember linear, the first order differential equations have the form y prime plus p of t times y is equal to q of t. First order separable differential equations have the form y prime is equal to g of t times h of y, which means we can gather the same variable into one side of the equation. For example, when you write h of y to the left hand side, and if you write dt to the right hand side, so you can see it is a separable differential equation. And first order autonomous differential equations have the form y prime is equal to h of y or f of y. Okay. Let y is equal to f of t be the population of the given species at the time t. Okay, here we will have a formula for determining the growth, the rate of the growth of the population. The simplest hypothesis concerning the variation of population is that the rate of change of the variable y is proportional to the current value of y. In other words, we can write dy over dt, which represents the rate of change of the population at the time t over y is over y. Is equal to r. Okay. Writing this form in this current form, dy over dt is equal to r times y, where the constant of proportionality r is called the rate of growth or decline, depending on whether it is positive or negative. If you have positive value for the constant of proportionality, so it's called the rate of growth. If it is negative, so we say that it is the rate of decline. Here we assume that r is positive, so the population is growing. Solving this differential equation subject to the initial condition y of 0 is equal to y0 at the beginning, the population is y0. So from here this is a separable differential equation because we can write 1 over y dy is equal to r times dt. From here, taking the integration of both sides of this equation, we can write ln y is equal to rt plus c, and from here y is equal to e to the power rt times the constant c1. Using the because we have e to the power c, which is a constant again, instead of e to the power c we write c1. Okay, Using the initial condition y of 0 is equal to y0, so we have y0 is equal to 1 times c1. So from here c1 is equal to y0. Writing y0 instead of c1, we obtain this solution. Okay. Therefore, the mathematical model consisting of the initial value problem above with r is positive predicts that the population will grow exponentially for all time. Okay. The population growth can be given exponentially using this solution of the differential equation. Okay. This is called the exponential growth of the population. For example, consider the growth of an amoeba population that doubles every hour. So let's describe its differential equation. At the beginning we have one amoeba. After 1 hour, according to the given information here, the number of amoeba will be 2 after 1 hour. After 2 hours, the number of amoeba will be 4 because the population doubles every hour, and so on. At time t, according to the information, the population will be 2 to the power t. Therefore, y of t is equal to 2 to the power t, which states the amount of the population for the amoeba according to the example. By taking the derivative of this equation, so we obtain dy over dt is equal to the derivative of 2 to the power t, which is equal to ln 2 times 2 to the power t. So 2 to the power t is y of t. Therefore, we obtain dy over dt is equal to ln 2 times y. Here, r is equal to ln 2. Okay, the constant of proportionality for this example is ln 2. Constant of proportionality. Okay, actually we know the amount of the population at the time t by using this equation, but the example wants to describe its differential equation. So taking the derivative from this equation, so we obtain its differential equation, which is an example of autonomous differential equations here. Okay, because the right hand side of the equation is just a function of y, also we have the constant of proportionality ln 2. Here we have some definitions. The equilibrium solutions of an autonomous differential equation are all of the constant of the form y of t is equal to k. Okay, a phase line we will see in the example in the following examples gives a quick description of the behavior of the solution. If a solution approaches the equilibrium solution as t goes to infinity, then the equilibrium solution is asymptotically stable. Okay, graphically, the upper side of the equilibrium solution, you see the behavior of the solution of the differential equation, namely the slopes are negative here, and here the slopes are positive. Therefore, the equilibrium solution is stable. Okay, stable. If a solution goes away from an equilibrium solution in both sides, then it's called unstable equilibrium solution. The solution is unstable. Namely here, the slopes are positive. Here the slopes are negative. If a solution approaches one way and depart from other, it is called semi-stable solution. Namely, here we have positive slopes. Here we have negative slopes, and we have also again positive slopes here. And this is the inverse version of the previous one. Okay. For example, to take account of the fact that the growth rate actually depends on the population, so we replace the constant r in the equation, namely y prime is equal to r times y, by a function of y, which is stated by h of y, and thereby obtain the modified equation dy over dt is equal to h of y times y. H of y is written for taking account of the fact that the growth rate actually depends on the population. The growth rate r is not a constant here. It depends on the population. Okay, it depends on the population. So here we have a special case for this modified equation by writing a minus r times y for h of y. Then the modified equation is called logistic equation, which states the logistic growth of the population. If you write a linear function with respect to y for the constant of the proportionality, so we obtain a special case such that the modified equation states the logistic growth of the population. Okay. For example, let's say h of y is equal to 3 minus 2 times y. 3 minus 2 times y. Namely, the modified equation becomes dy over dt is equal to 3 minus 2 times y times y. The proportion of the equation is a function of y, which is a linear function, 3 minus 2 times y. Okay, this is an example of logistic growth of the population, which okay, this is a differential equation. So here we will investigate the definitions written here for this example. First, we need to find the equilibrium solutions. You know, equilibrium solutions can be found by writing 0 for the derivative. So we write 3 minus 2y times y is equal to 0. So from here we obtain y is equal to 0 or y is equal to 3 over 2. And from here we will find the phase line to see the behavior of the solution quickly. So the equilibrium solutions are y is equal to 0, y is equal to 3 over 2, and the differential equation is 3 minus 2 times y times y. Okay. So we should find the sign of the first derivative. 0, 3 over 2. So what is the sign of the first derivative if the value of the variable y is bigger than 3 over 2? For example, when we take the number 2, so we obtain negative value for the parentheses, and this is a positive value, therefore we obtain negative value for the first derivative. Between 0 and 3 over 2, for example, when we take 1, we get a positive value, therefore we have positive values between the equilibrium solutions, and here we have negative values. Why do we find the sign of the first derivative? Therefore, because we describe the value of the slopes actually can be negative or positive. So after that we will determine the phase line of the equation, phase line. This is the number 0, this is the second equilibrium solution, 3 over 2. So for all values of y bigger than 3 over 2 we have negative slopes, therefore the direction will be in the negative side, like this one. Okay, direction will be in the negative side. Between 0 and 3 over 2 the direction will be in the positive side, and similarly for all values of y less than 0, direction will be in the negative side. So you see the solution, the equilibrium solution y is equal to 0 is unstable because according to the definition written here, the solution goes away from an equilibrium solution. Okay, therefore we say it is unstable by using the phase line. And the solutions are approaching to the number 3 over 2 from the right hand side and from the left hand side. Therefore we say this is a stable solution, stable equilibrium solution. Also you can see from here number 0, 3 over 2, 3 over 2. So for all values of y we have negative values for the y prime, therefore we have negative slopes, which means the curves will be in this form to get negative slopes for the tangent lines. Okay, and between 0 and 3 over 2 we have positive slopes, therefore the solution curves will be in this form. Okay, and for all values of y less than 0 we have negative slopes, therefore to get negative slopes for tangent lines, if you remember, the directions will be in this form. So here you see the equilibrium solution y is equal to 3 over 2 is stable equilibrium solution, stable equilibrium solution, and for 0 we have unstable equilibrium solution, unstable. Okay, this is typical solution curves actually. For example, when we sketch a tangent line at this point, so we will have negative slope because of its direction, therefore we sketch a curve in this form when we have negative values for the first derivative. Similarly, when we sketch a tangent line for this curve like this one at this point, so we will have positive slopes, therefore the direction of the curve will be in this form, and so on. And easily you can find the general solution of this logistic differential equation. This is a separable differential equation. This is your homework. Please solve this equation, and when you have any question you can ask me, you can send any email, and so on. Another example, find the equilibrium solutions and sketch the phase portrait of the differential equation. Y prime is equal to y squared times 4 minus y squared, classify each equilibrium solution as asymptotically stable, unstable, and semi-stable. First, let's find here. Write the differential equation y prime is equal to y squared times 4 minus y squared, 4 minus y squared. First, we need to find the equilibrium solutions. The derivative should be 0, which means y squared is equal to 0, and 4 minus y squared is equal to 0. From here we have 0 for y, this is double root, okay, and from here we have plus minus 2. They are the equilibrium solutions of the differential equation, and we should find the sign of the first derivative according to these results. Minus 2, 0, 2. 0 is double root. And 2. So from here, when we take a value bigger than 2 in this equation for y, for example, let's take 3, so the parenthesis becomes a negative value. This is a positive value, so we have negative value. From 0 to 2, for example, when we take the number 1, so the parenthesis becomes a positive value. This is a positive value, therefore we have positive value. Between minus 2 and 0, for example, minus 1, again we have a positive value for the parenthesis, and this is a positive value, therefore we have positive slopes. And when we take a value less than minus 2, for example minus 3, we have a negative value for the parentheses. This is a positive value, product of them will be negative. Okay. When we want to sketch a phase line, so we have minus 2, 0, 2. So for all values bigger than 2, we have negative slopes, therefore the direction will be in the negative side. Between 0 and 2, we have in the positive side. We are in the positive side. Between minus 2 and 0, we are still in the positive side. Less than minus 2, we are in the negative side. We are in the negative side. So we can see easily minus 2 is an unstable equilibrium solution. Because the solution curves are going away from the equilibrium solution. 0 is semi-stable because on the left hand side the solution curves are approaching, but in the other side the solutions are going away from this solution, so we say semi-stable, and this is stable because solutions curve are approaching the number 2. Also we can see by sketching a typical solution curves. So we have minus 2 to 0, 2, 0, minus 2. This is the equilibrium solution. This is another one. So we have negative slopes for all values of y bigger than 2. So we sketch a typical solution curve like this, and we have positive, which means this is the typical graph, and we have positive slopes, therefore the direction will be in this form, and we have negative, therefore we sketch a typical curve in this form. So you see the number 2 is a stable equilibrium solution, 0 is semi-stable, and minus 2 is unstable. Equilibrium solution. Thank you very much.